One of the most important advances in the early part of the 17th century was the introduction of analytic geometry. So what do we mean by analytic geometry? Well, analytic geometry connects arithmetic and algebra with geometry via coordinates of points on a number line and coordinates of points in an xy plane. This is called the Cartesian coordinate plane in honor of Rene Descartes, who was the founder of it, or at least one of the founders of this idea. There were actually two prominent mathematicians, both French, who did work in this more or less same area at the same time, Rene Descartes and Pierre de Fama. And we'll talk about each of them in just a little bit. So if we think back to the Greeks did algebra and arithmetic using geometric means. Everything was thought of geometrically. Let's go even further back. If you go even further back to say the Mesopotamians, some of the earliest folks that we have records of doing any kind of serious mathematics, they solved some problems sort of algebraically. They solved some geometric problems. We don't know a lot about their techniques, but we do know some of the things about the kinds of problems they were able to solve. If you go forward to the Greeks, they had a revolution in the way they thought about mathematics, and geometry became the ideal, and this axiomatic approach where they worked on proofs was very important. They also still continued, however, to solve some what we would probably call algebraic type problems or problem solving, or they did arithmetic some. But of course, the way they thought of that, to them, a number was basically something you could measure geometrically. So everything that was done there, when they talked about solving equations, they were talking about doing some sort of geometric construction. They didn't really talk about equations, so to speak. That was a later thing. Now you fast forward some centuries, and with the Islamic mathematics, we start to see algebra lifted out and separated from geometry, although it's still connected. So geometry there was used to prove sort of the algebraic results, but they started to think of the algebra as doing separately from geometry. So it didn't start separate, but it started to separate over time. And then when you get into the Renaissance period in Europe, now algebra has started to move outside of geometry and sort of existing on its own, so that solutions were done in algebra without any reference to any kind of geometry or pictures or anything. And now with analytic geometry, you're kind of coming full circle. So analytic geometry now connects the algebra back to the geometry, but in such a way that we're thinking of sort of the algebra as being the tool that might help us solve geometry problems. See, that's exactly backwards from the earlier result, where geometry was used to solve things we might think of as algebraic problems. This is going the other way. We might start with a geometric problem and use it solving algebra. So we've kind of come full circle here. And this idea is so pervasive in our modern understanding of algebra and calculus and so forth that it's hard to realize what a big deal this was at the time, and how revolutionary it was. So basically the idea here, of course, of a coordinate system like we have here is you have a number line and you can find points on that number line, right? And this number line includes negatives, has positives, but may have started out with mainly positive ones. We could extend to negatives. We could make sure we're talking about a continuous line here. So this would include all numbers, not just rational numbers on this line, all real numbers. And the same way for a perpendicular number line here, and we can locate points in the plane, like this is a point 3, 4. It's lined up with 3 on the first axis, 4 on the left, on the vertical axis. So in other words, we could go from the origin here, go right 3 and up 4. Now, when Descartes and Fermat did this, they did not necessarily insist on this second axis being perpendicular to the first, but they did say we could find things, lines in the plane and points in the plane, in reference to two lines, to their positions to two lines. And of course, it's become a modern convention and convenient to make them perpendicular. Now, of course, along with this comes, well, what about ordered pairs that solve a solution to some equation like y equals x squared? And now we graph things like this. So this would be a little bit later thing, but something that Descartes and Fermat were working on at that time. And again, this is so pervasive of our modern understanding of calculus and algebra that we look at things in what's called the rule of four now, where we look at a relation or function like y equals x squared. We might represent that as a formula here. We might represent that as a graph that we see here. We might represent that as a set of ordered pairs in a table, and we might explain that in words as well. And of course, it may be done in some sort of real world context as well. So there's all those things are different ways to look at that. And this idea that Descartes and Fermat worked on has really changed mathematics, and it really set the stage for doing calculus later on. So just a little background about these two individuals. Rene Descartes was born in 1596, died in 1650. So right there in the first part of the 17th century he lived and worked. He was a French mathematician and philosopher. I mentioned in the previous video that he is known as the founder of modern philosophy. So he is a very important philosopher as well as mathematician. He attended Jesuit college, La Flèche, in Anjou, starting at 11 years old. He eventually got a law degree, mainly at the encouragement of his father, at the University of Poitiers in 1616. He did some military service of different kinds, which got him traveling around Europe for a bit, ended up settling in Holland. As I said, he was very influential in the establishing philosophy. One of the things he attempted to do was find a philosophical basis for all knowledge and felt that everything should be based on mathematical principles. He did write a major treatise on science with appendices on optics, meteorology, and geometry. His meteorological book was the first to put the study of weather on a scientific basis. So he's very important as the founder of modern meteorology. The most significant was his La Geometry, which included some various things, including theory of invariance, and the idea that algebra can be used to solve problems in geometry and to see multiple geometric problems as related. And analytic geometry allows for solutions to problems posed geometrically that can't be solved geometrically. At about the same time and close to the same age was Pierre de Fama, born in 1601 and died in 1665, just slightly younger. French lawyer and government official. He was an amateur mathematician. He never really had a job as a mathematician. He worked for, like I said, as a lawyer and worked for the government in a variety of capacities. He did a lot of work in number theory, analytic geometry, and foundations of calculus. Descartes also worked on some foundations of calculus. And he had similar ideas about analytic geometry as Descartes. He worked on tangents, which of course leads to one of the big parts of calculus. He was also the co-founder of probability theory through a series of letters that he exchanged with Pascal. So he and Pascal are credited with founding the theory of probability. He's probably most famous in a way for some of his work on number theory. One thing in particular is Fermat's last theorem, that x to the n plus y to the n plus z to the n has no integer solutions for natural numbers for n greater than 2. We'll talk more about this in the number theory video here in just a little bit. This wasn't actually formally proved until 1994 by Andrew Wiles. And we'll come back and talk about that in a bit in another video. Okay. Both independently at the same time, Fermat and Descartes developed similar methods of what is now known as a Cartesian coordinate system. The axes didn't initially have to be perpendicular like we use them today, but there's a difference in the way they approach some things. For one thing, Descartes published He published philosophy. He published mathematics. So that meant it was, they didn't have a lot of like research journals like we have now, but they would publish something like what we might call a monograph, and it would be printed and distributed. That got it out to a much larger audience and more public. Fermat had a different style, being more of an amateur mathematician, meaning he had a full-time job doing other things. Mathematics was still kind of his passion, but he communicated mostly through letters and manuscripts that were not printed, but rather handwritten. That made them less important in the sense of being influential to other folks because they just weren't as widely distributed. Um, so the manuscripts of Fermat's advances in analytic geometry actually made their way to Descartes just before Descartes' results went to press. So, so there's some question about which one, was actually the first to come up with some of these ideas, but of course Descartes' ideas got out to the public a little bit, the general public a little bit faster than Descartes, than Fermat's, but Fermat's actually made their way to certain individuals before Descartes went to press. So there's some interesting controversy there. Now, Fermat studied with students of Viète, and so he ended up using Viète's notation for algebra, which was a vast improvement over some things that came before, as we talked about back in the Renaissance videos. But Descartes actually improved upon the notation of Viète, and among other things, he used the modern naming convention for variables, letters from the end of the alphabet for variables, and in unknown constants used letters from the first of the alphabet. That's pretty much what we normally do today. And he freely multiplied quantities of different dimension without really uh, paying much heed to that. Back in the days of the ancient Greeks, it didn't make sense to talk about multiplying a line and a cube. So something that was, first dimension versus third dimension didn't make sense to do that. And Descartes had no problem multiplying cubes of things times linear things. He didn't have any trouble multiplying an x cubed times an x, for example. Um, The way they approached analytic geometry was also a little different. For Descartes, geometric curves were the uh, the the starting point and the main thing to look at. So he mainly looked at geometric curves, and then from that he was able to try to derive some equations for those curves. Fermat sort of took the opposite approach. He started with the equations, and then they were sort of primary importance, and then he was able to graph the curves. Now, they eventually became publicly critical of each other's works and had an unfortunate rivalry and feud there, with even one of them calling out the other as being, as their works not being on a sound reasoning and so forth. And of course, these things, became public. So here's another example, like the Tartaglia uh, Cardano feud that we talked about in the Renaissance. Here's another feud between two prominent mathematicians doing similar things at the same time. But in any event, Fermat and Descartes were both very influential, very prominent mathematicians of the early part of the 17th century, and they did a lot to advance mathematics in various ways when you put them together, not only in analytic geometry, which was the main point of this particular video, but also in probability theory, in theory of equations, in notation, in working with tangents, and eventually setting the stage for the development of calculus.